Welcome back to Differential Calculus. In this video, I want to review solving inequalities. Unlike every other video in this review, there should be nothing new as far as notation or process compared to things that you've learned in previous mathematics courses. I feel very confident in saying that everyone has been taught how to solve inequalities in pretty well the same manner. The one thing that I worry about is that inequalities tend to be an afterthought in a lot of lower level courses. Sure, it's something that you talked about for one day and then you moved on and kind of never thought about it again. The foundations of calculus are all built around working with inequalities. And so before we get into any of the new material, I want to make sure that everyone is on the same page and everyone remembers how all of these processes work. Let's get my head out of the way and let's just dive right in. How about 17 minus 5x is greater than or equal to 3. In order to get x by itself, I first want to subtract 17 from both sides of the equation. That gives me that negative 5x is greater than or equal to negative 14. And then to get x by itself, I want to divide both sides of the inequality by negative 5. And we're dividing now by a negative number. Remember that whenever you divide by a negative number, it changes the direction of the inequality symbol. So we go from having a greater than or equal to having a less than or equal to. Negative 14 divided by negative 5. Yes, you could get a decimal approximation, but this is calculus, this is math class, so we're generally going to be happiest with the improper fraction. I will leave this as 14 over 5. I'm never going to explicitly ask you to graph the solution to an inequality on a number line, but I think it's worth taking a moment to think about. Most of the time that's a fairly straightforward ask, but every now and then you get an inequality that's set up a little bit strangely, and you have to take a few minutes to make sure you understand it. I will ask you to look at your solution to the inequality and rate the solution set in interval notation. In this case, looking at my graph, I can see that it continues onward indefinitely. So that's negative infinity on the left-hand side. On the right-hand side, it goes to 14/5, and it is closed on that side. All right, there we go. Let's make this strictly less than. X squared plus 5x plus 6 is strictly less than 0. This is a nonlinear inequality. And so we have to be a little bit careful about it. Some of the things that I've seen frequently is let's stop thinking about the inequality and think about the related equality for just a few moments. X squared plus 5x plus 6 equals 0 is fairly straightforward to solve. We can factor that left-hand side. It factors to x plus 2 times x plus 3. We can use the zero product rule. X plus 2 equals 0, or x plus 3 equals 0. We can then solve each of these. X equals negative 2, or x equals negative 3. And why did we do that? Well, we know that if you want to transition from being greater than 0 to being less than 0, or from being less than 0 to being greater than 0, you have to pass through being equal to 0. And so if we think about where these fall on a number line, negative 3 and negative 2 right here. If I pick any point to the left of negative 3, like say negative 4, and I plug that into the original inequality, Negative 4 squared is positive 16. 5 times negative 4 is negative 20. And negative 16 plus 20 plus 6 is positive. Positive numbers are not less than 0, so this part of the number line is not part of the solution. If I check something over here to the right, like say 0 itself, I have 0 squared plus 5 times 0 plus 6, which is 0. Which is 6. 6 is not less than 0. That's a positive number again. So that is also not part of the solution. Then I check somewhere in between. I save this for last because there's no nice number. I guess I'll look at negative 2.5. And at this point, I'm probably grabbing out a calculator. Negative 2.5 squared is 6.25. 5 times negative 2.5 is negative 12.5. And so we have all told negative 0.25, which is negative. A negative number satisfies the inequality. And we know that we cannot transition from negative to positive without going through 0. And we know that 0 happens at negative 3 and at negative 2. Finally, I look at the kind of inequality. It is strictly less than, which means we do not want the places where this is equal to 0. I will use an open bracket on both sides, and the solution set in interval notation is the interval from negative 3 to negative 2. The solution to the inequality is negative 3 is less than x, and x is less than negative 2, which you could combine and write as negative 3 less than x less than negative 2 if you so desire. Speaking of three-piece inequalities, when you have variables hiding in these, it gets a little bit trickier. So if I have something like negative 5 is less than 2x plus 7 is less than, 13. The process is the same here as it is for a two-piece inequality, except that now you have three pieces. There are three sides to subtract. I need to get rid of the plus 7, so I subtract 7 on all three sides of the inequality. Negative 12 less than 2x less than 6. I need x by itself, so I need to divide by 2. And I'll need to divide by 2 on all three sides of the inequality. Negative 6 less than x less than 3. I can sketch that on a number line as well. This one is fairly straightforward. It is open on both sides, contains all the stuff in the middle, and in interval notation, this is the open interval from negative 6 to 3. The last one that I want to look at is absolute value. The absolute value of 3x plus 5 is less than or equal to 17. This is a nonlinear inequality, so you can do the same thing with this that we did with the earlier example. You can think about the related equality, absolute value of 3x plus 5 equals 17, which means that either 3x plus 5 equals 17 or the opposite of 3x plus 5 equals 17. Those are both fairly straightforward to solve. And I get that x is either 4 or negative 22 over 3. One of the things that I do want to point out as I quickly sketch through, writing out the number line, recognizing that we're going to have all the stuff in between, including, no, that's not what I wanted to write, including the endpoints this time. So I have here my interval notation is the open interval from -22/3 up to 4. Right, I raced through. I didn't show you how I tested to the left, center, and right, because there's one really nice thing that you can know about absolute value. Whenever an absolute value inequality is less than or equal to, it is always going to include the stuff in the middle and not the stuff on the sides. Whenever an absolute value inequality is greater than or equal, it will always include the stuff on the outsides and never the stuff in the middle. Sometimes we use that to our advantage. So just as a quick reference, the absolute value of x less than b, opposite of b less than x less than b, these two statements are equivalent, and very often if you are looking at references talking about calculus, the author will switch between them without any warning whatsoever. It's really frustrating when you're trying to learn something new. Wait, there was an absolute value, where did it go? So just as a warning to you, this is something to pay attention to and make sure that you're noticing. I try to avoid this sort of thing in my lecture videos. I will slip up because I've spent enough time thinking about these things that those sorts of transitions are second nature to me. But that's not the interesting thing. The interesting thing here is actually solving the inequalities. So let's end with one for you to try. How about the absolute value of, not 3x, I just did a 3x. How about 5x minus 7 is greater than or equal to 15. Right? Important here. Solve the inequality, give the solution set in interval notation. Take a few minutes, see what you can do with that one, and I'll see you in the next video.